Bismillahirrahmanirrahim. I am Dr. Asad, lecturer, Institute of Numerical Sciences, Cohort University of Science and Technology. Dear students, welcome to the course of Calculus 1, course code MATH-101. We are in lecture number 9, and this lecture we will discuss limits and its applications. In the previous lecture, we discussed the definition of limit and also discussed the limit of constant and identity functions. Further, we provided some examples of those functions that have no limit in their domain. And also we discussed the laws of limit and provided some examples with the use of these laws. In outlines, in this lecture, we will try to discuss the following points. Number 1, statement of the sandwich theorem. We will discuss the statement of sandwich theorem without going to its proof. Number 2, applications of the sandwich theorem. Number 3, indeterminate forms. We will discuss two types of the indeterminate forms in this lecture, that is 0 by 0 form and infinity by infinity form. We will provide some examples and explain indeterminate forms by using the limits. Number 4, left and right hand limit. So we will discuss the limit of functions, that is the existence of a limit, by using the left and right hand limits. Number 5, there will be some practice problems to the students, and finally there will be references. Now the sandwich theorem. Suppose that f of x is greater than or equal to g of x and f of x is less than or equal to h of x for all x in some open interval containing the point c, except possibly at the point x is equal to c itself. Then assume that the limit of the function g of x at this point x is equal to c and the limit of the function h of x at the same point c is equal to L. Then the limit of the function at the point x is equal to c will be equal to L. In sandwich theorem, you will require three different functions, that is in this order, that is f of x will be greater than or equal to g of x and f of x will be less than or equal to h of x. Now if the limit of the function g of x and the limit of the function h of x is the same, that is in this case this is equal to L, then the limit of the function f of x will also be equal to L. Here except possibly at the point x is equal to c means that in limits we know that it is not necessary that the function is defined at that point at which we are finding the limit. Now to understand the sandwich theorem graphically, we are given three different functions here, that is f of x, g of x and h of x. Here you see that the function f of x is in between the two functions g of x and h of x. Now the limit of the function g of x at the point c is L, and also the limit of the function h of x at the point c is equal to L. Then the limit of the function f of x at the point c is also equal to L. Now in sandwich theorem, it is clear that the function must be in between the two functions, that is in this case h of x and g of x. Now in applications of the sandwich theorem, here we present a simple example, that is example number 1. Given that u of x is greater than or equal to 1 minus x square divided by 4 and less than or equal to 1 plus x square divided by 2 for all x not equal to 0. Now what we will do, evaluate the limit of the function u of x as x tends to 0, no matter how complicated the function u is. In solution, we will use the sandwich theorem, so that's why we will find the limit of this function and then the limit of 1 plus x square divided by 2. So the limit of the function 1 minus x square divided by 4 when x tends to 0 is equal to 1. when we use the limit x is equal to 0, we get this function is equal to 0, and we will get only constant which is equal to 1. And similarly, the limit of the function as x tends to 0 of 1 plus x squared divided by 2 is equal to 1. Here also this term will be equal to 0, and we will get only the limit 1. Now, by using the sandwich theorem, the limit of the function g of x and the limit of the function h of x is equal to 1. So the limit between the two functions in this case, which is u of x, is equal to 1. So applying the sandwich theorem, we get that the limit of the function u of x as x tends to 0 is also equal to 1. Now, how to explain the previous example graphically? Here we present a diagrammatical representation of the previous example, in which the function y is equal to 1 plus x squared divided by 2 is plotted. It is the uppermost curve, and similarly the function y is equal to 1 minus x squared is plotted. It is the bottommost curve, and we will find the limit of the function y is equal to u of x. Since the limit of this function at the point x is equal to 0 is 1, and also the limit of this function when x tends to 0 is equal to 1, then using the sandwich theorem, the limit of this function at the point x is equal to c, you can see that this also equal to 1. Now, continuing the applications of the sandwich theorem, in example number 2, we are given a graph of three different functions in which y is equal to absolute of theta and y is equal to minus absolute of theta are plotted, and the graph y is equal to sine theta is plotted in between the two graphs. Now, what we will do, we will find the limit of the function y is equal to sine theta as theta tends to 0. In solution, we will use the definition of sine theta. So we have, this is from the basic calculus, sine theta is always greater than or equal to minus absolute of theta and is less than or equal to absolute of theta for all theta. Now, since the limit of minus theta and the limit of absolute of theta is equal to 0 as theta tends to 0. Now, the limit of this function is 0, and the limit of this function as theta tends to 0 is also equal to 0. Now, applying sandwich theorem, the limit of this function sine theta will also be equal to 0, because the limit of this function and the limit of this function is equal to 0. Indeterminate forms. In this lecture, I will discuss only 0 by 0 and infinity by infinity forms. In the later lecture, we will go through some other indeterminate forms. So we will handle only two forms in this lecture, that is the 0 by 0 form and infinity by infinity form. I am explaining these two forms by using a suitable example. Here I am presenting two different parts in example number 3. That is, in part 1, limit x tends to 2, x square plus x minus 6 divided by x square plus 2x minus 8. And in part B, the limit delta x tends to 0 of the function delta x whole square plus 2 delta x divided by delta x whole square plus delta x, where delta x is a variable in this case. Now, in solution of the part A, if we use directly x is equal to 2 in the function, this is a rational function, so we will get 0 by 0 form. So the numerator and denominator are both equal to 0 at the point x is equal to 2. So what we will do, now we will factorize the numerator. So we will get two linear factors, that is x plus 3 and x minus 2. And similarly, factorizing x square plus 2x minus 8, we will get two linear factors, x plus 4 into x minus 2. Now, since we will take x not equal to 2, so we can cancel x minus 2 with x minus 2. We will get x plus 3 divided by x plus 4. Now, applying the limit as x tends to 2 on the function, that is x square plus x minus 6 divided by x square plus 2x minus 8, And since this is equal to x plus 3 divided by x plus 4, so we can also apply the limit on this function. So using the limit, we will get 2 plus 3 divided by 2 plus 4, which further is equal to 5 by 6. So the limit of this function is equal to 5 by 6. But since this function is also equal to the original function, so we get the limit of the original function, that is x square plus x minus 6 divided by x square plus 2x minus 8, which is equal to 5 by 6. Now in part B, the denominator also vanishes when delta x is equal to 0. And similarly, the numerator is also equal to 0 when x tends to 0. Now, in the numerator, if we common delta x, we get delta x times delta x plus 2 and divided by delta x square plus delta x. So we can cancel out the delta x in the denominator and we will get delta x plus 2 divided by delta x plus 1. Now applying the limit on this function, we get 2 divided by 1, which is equal to 2. Since the limit of this function is equal to 2, and this function is the simplified version of the original function, so the limit of this function is equal to 2. In example number 4, here we are given three different functions, that is the limit of the function 1 over x at the point x tends to infinity. In part B, limit x tends to infinity of the rational function 2x plus 1 divided by 3x plus 1. And in part C, limit x tends to minus infinity of the function 5x square minus 3x plus 2 divided by x square plus 1. Now in solution, when x tends to infinity, 1 over x is equal to 0 because we increase the value of x. So we will get 1 by 2, 1 by 3, 1 by 4, 1 by 5, and as x tends to infinity, this function 1 over x goes to 0. So in the limiting case, we can write that limit x tends to infinity, 1 over x is equal to 0. Now to evaluate the limits in part B and part C, if we use direct the limit x is equal to infinity in this function, we get 2 times infinity plus 1 divided by 3 times of infinity plus 1. Now 2 times of infinity is also infinity, and if we add something to the infinity, we get also infinity. So we get infinity divided by infinity form. Now what we will do to evaluate this limit? Now taking common out x from the denominator and also taking common x from the numerator, we get 2 plus 1 over x divided by 3 plus 1 over x, and x will be cancelled with x in the denominator. Now applying the limit in this function, so we get 1 over infinity, which is equal to 0 as discussed in part A, and similarly the limit of 1 over x is also equal to 0 as limit x tends to infinity. So we get 2 plus 0 divided by 3 plus 0, which is equal to 2 by 3. So the limit of this function as x tends to infinity is equal to 2 by 3. Now in part C, limit x tends to minus infinity, 5x square minus 3x plus 2 divided by x square plus 1. If we use the limit x is equal to minus infinity, we get minus infinity square and minus 3 times of the minus infinity, which is also equal to positive infinity. So we will get infinity in the numerator, and also if we use x is equal to minus infinity in the denominator, we get minus infinity square, and adding 1 with minus infinity is also equal to infinity. So we will get infinity by infinity form. Now taking common out x square from the denominator and the highest degree variable, that is x square, from the numerator, these x square and x square will be cancelled with each other. So we will get x tends to minus infinity, 5 minus 3 by x plus 2 divided by x square divided by 1 plus 1 over x square. Now when x tends to minus infinity, minus 3 by x is equal to 0. And similarly, when x tends to minus infinity, this 2 by x square is also equal to 0. And in the same fashion, the limit of 1 over x square as x tends to minus infinity is also equal to 0. So we will get 5 divided by 1, so which is equal to 5. So the limit of this function as x tends to minus infinity is equal to 5. Here we discussed infinity by infinity form. So what we will do in infinity by infinity form, we will take common out the highest degree variable from the denominator and also from the numerator, and then after simplification and applying the limit, we will get the required result. Now, to understand the existence of a limit, here I am presenting two different graphs, that is for the right hand limit and for the left hand limit, both defined in part A and part B. Here you can see that limit x tends to c f of x is equal to L, and the positive sign in the power of c denotes the direction of the limit. It means that we are approaching the point C from the right side, and the function value goes towards the capital L. So limit x tends to C from the right side if of x is equal to L, while in part B, limit x tends to C, that is negative sign in the power of C, shows again the direction of the limit. In this case, this is the left limit, that is we are approaching towards the point C from the left side. The function value goes towards capital M. So in the left limit, limit x tends to C, f of x is equal to capital M. Now for the existence of the left limit and the right limit must be equal. If the limit of the right hand side is equal to L and the limit on the left hand side is also equal to L, then we say that the limit of the function exists at the point x is equal to C. Now, graphical discussion by using the left hand limit and the right hand limit. This is just a simple example of the function s is equal to f of t, and this is the graph of this function. Now, to evaluate the limit at the point minus 2, if we approaches this point minus 2 from the left side, the function value goes towards 0. And if we approaches towards the point minus 2 from the right side, the function value also goes towards 0. So the left limit and the right hand limit is equal to 0, and thus the limit exists and is equal to 0. Now to find the limit at the point minus 1. So approaching minus 1 from the left side, the function value goes towards minus 1. And approaching towards minus 1 from the right side, the function value also goes towards minus 1. So both the left and right limit are equal, and thus the limit exists at the point minus 1, and which is equal to minus 1. Now we can approach this point 0 from the left side and from the right side. Approaching 0 from the left side, the function value goes towards minus 1. While approaching towards the point 0 from the right side, the function value goes towards positive 1. So the left limit is minus 1 and the right hand limit is equal to positive 1. Left limit and right limit are not both equal, and thus we say that the limit does not exist at the point t is equal to 0. In example number 5, we are to evaluate the limit of the function x divided by x absolute at the point 0. Now the graph of the function here is plotted as, when we are approaching towards the point 0 from the left side, by definition of the x absolute is equal to minus x. So cancelling x with x, we get minus 1. So the left branch of the function is minus 1. And similarly, when we are on the right hand side of the point 0, we get x absolute is equal to x, and we cancel x with x, which is equal to 1. So the right branch is just a simple 1. Now to find the limit at the point 0, we can approach this point 0 from left side and from right side. Now approaching the point 0 from the left side, the function value goes towards minus 1. And when we are approaching towards the point 0 from the right side, that is from the right side towards the point 0, the function value goes towards the positive 1. So the left limit is equal to -1 and the right limit is positive 1. Now both the left limit and the right limit are not equal, and thus we say that the limit does not exist at the point 0. Now to understand the topics discussed in this lecture, here I am presenting some practice problems to the students, that is problem number 9 to problem number 20. Students are requested to solve these problems as their homework. If they feel any problem in these problems, so they can contact me on my email given at the footnote. Finally, in references, all the materials in this lecture are provided from the Thomas Calculus, including second order differential equations, 11th edition. Now in conclusion to this lecture, in this lecture we provided the statement of the sandwich theorem and also provided some applications. Further we classified the indeterminate forms, that is the 0 by 0 form and infinity by infinity form, by using some suitable examples, and also discussed the left hand limit and right hand limit geometrically. And at the last, some practice problems are provided to the students.